Now I'd like to introduce Dr. Ricardo Lima. He's a research scientist in the Extreme Computing Research Center, or ECRC, working with Professor Omar Neo here at King Abdullah University of Science and Technology. He'll be discussing path planning and uncertain transient currents. So without further ado, please welcome Dr. Lima.
Thank you, Ryan. Thank you very much for the introduction. So first of all, this work is the result of a team. The team is Sultan, Thomas, Luik, Ibrahim, and Omar Neo. That is our group leader. So in my first meeting, the first time I had a talk and a discussion with Eric, he asked me, "So what do you do?" And I told him, well, we develop trajectory planning models for underwater vehicles. And immediately the second question was like, "So do you throw them to the water? Do you do experiments?" And I told them, "No, unfortunately, we are not the lucky ones that are diving with these gliders. So what we do, in fact, and we are excited about that, despite that we are not diving with them, we develop some trajectory planning models for AUVs, for underwater vehicles. And in fact, here at KAUST, there are some gliders in the Red Sea Research Center. We had an excellent presentation as the first presentation of this session with lots of applications of AUVs. So when we think about applications of AUVs, we think about mapping the seafloor as well as it was shown in the first presentation, right? To explore extreme environments for military applications, but also for oceanographic research, right? Here at KAUST, we have the Red Sea Research Center, where these gliders are used for Red Sea sampling. They are important to forecast biological or ecological process and to improve ocean forecasts. In the operations, the operations or the areas involved in AUV's operations are many, as we can see in this figure. You have here the practice, the ocean science, right, where they are concerned with biology, oceanography. Then we have areas like robotics that work on controls, developing of controls, sensors, networking and communication, sampling, statistics, and where we are working, our focus is here on trajectory planning. We are developing optimal trajectory planning solutions that can contribute to improving efficiency and increase the autonomy in terms of battery, in terms of energy consumption of these vehicles. There is another field that deals with replanning that is more linked with the awareness capabilities and autonomies of these vehicles. It is more online, and that requires fast algorithms to deal with a complex and dynamic environment. So at the level of trajectory planning, what we are concerned with is to develop to find a trajectory, and in this trajectory involves a path and the timing of the waypoints across this path. So in our trajectory planning models, what we have is a high uncertainty level, very low detail level in terms of the characteristics of the vehicle, and low time resolution, meaning that we have a time resolution sometimes of 1 hour, 2 hours, right? When you go to more to the control area, at that time you have less uncertainty, you have more level of detail of the vehicle, and you have a smaller time step. But in our case, we are working here at the level of trajectory planning. And what is the problem statement of this trajectory planning problem? So generally, and then we are going to see some specific cases, generally, we are given the initial position and the target position. What is the initial position and the destination? What are the initial conditions of the vehicle? The coordinates of the obstacles, and then also bounds on the vehicle speed and acceleration, and the flow field where the vehicle will navigate. And we want to determine the trajectory, meaning the path, the sequence of waypoints, but also the motion results in terms of velocity, acceleration, and timing, in order to minimize the travel time from the starting point to destination and or the energy consumption. So the general formulation for this problem is a kind of optimal control formulation, where we want to minimize the trajectory time, subject to some kinematic constraints, initial and final conditions, bounds on velocity and acceleration, and we want the vehicle to navigate in the domain free of obstacles, right? So this is our general problem formulation. Our first approach, our first optimization framework to deal with this problem, in fact, was based only on a 2D mixed integer nonlinear programming formulation. Basically, what we did initially was to pick the models developed for unmanned aerial vehicles developed by Eric, in fact, and extend those MLP models, mixed integer linear programming models, to handle a non-linear flow. And that is what we have here in this figure from one of our works, where we start here on the left. We want to go to the target, and we have 3 obstacles, and we have a flow. The shortest path and the fastest path without any flow is going through this path here. But then when you add the flow, the path can be different. And so what we did was we developed different models with different levels of details, and we tested different models and we optimized. And this was the kind of solutions that we are obtaining. For example, the best solution here is the one with the red dots and red line. That is, in fact, our most detailed model. But in this type of formulation, what we had was only a 2D formulation, and with binary variables to avoid the obstacles and to detect the arrival of the vehicle to the target. We had also some disjunctive programming formulation to model these obstacles and the arrival detection. But in fact, what we wanted was to move from this synthetic case study to the real world, to the Red Sea, right? So what are some of the research challenges when we try to go from this type of formulation and case study to the real world? So our first challenge was to develop a non-linear trajectory optimization framework without the binary variables, but that we can handle realistic 3D steady ocean currents and some strategy to avoid the obstacles. And so this was the first research challenge that we wanted to overcome. Then we thought, okay, now what we would like to do is to extend this framework to include multi-objective time energy optimization, but also include 3D time varying currents. And the third one, that is the third part of this talk, is how can we build a stochastic optimization formulation for this kind of problem that takes into account the uncertainty of the current. And so these research challenges are in fact reflected in the table of contents that we have here. So I will first start with a nonlinear trajectory planning, move to the multi-objective, and then go to our stochastic optimization formulation that includes some risk awareness, as you are going to see. So in this first challenge, we want to address how do we include the current of the Red Sea and the obstacles in a non-linear programming optimization framework, right? And that is what I'm going to show you in the next slides. So our first challenge was to build a function that describes the current field in the Red Sea. And so what we did was we built a smooth function, a function that is smooth and differentiable, that can be used by our NLP solvers. And for that, what we do is we use data from an ocean general circulation model. And so what we did, in fact, was we created a software function, right, that encapsulates a tricubic interpolation in 3D of the OGCM nodal values, right? So we get a matrix with a velocity vector on a discretization of the space, 3D. And then what we have is a function that receives any position receives a position in this domain and give us what is the velocity vector in 3D. And so this is an interesting function because it provides the current, the gradient, and the SN values that we need for the NLP solver, right? It has these key features for the NLP solvers. So with this strategy, we were able to handle the current, right? Then we need to handle the obstacles. In our first approach, right, we use the binary variables, but when we start moving to the Red Sea, we started to see that it was difficult to build this strategy with the binary variables applied to the real world Red Sea, for example. And so what we did was the following. We are going to explore the topography data that we have from the OGCM. And so we have this matrix with the discretization of the space and with the vectors of the velocity. And what we are going to do is we are going to associate a value, assign a value of 1 for the nodes that are in the fluid, and -1 for the remaining that are the obstacles. It can be land or it can be the seafloor. And so here in these figures on the left, what we have is a discrete classification of the data with 1 and -1. But in fact, what we need is a smooth function, right, that we can use in our nonlinear optimization. So what we did was we interpolated all the values between the 1 and -1 to get a function like what is here on the right, where you see that the -1 is this kind of reddish and 1 now is this kind of yellow. So in fact, we have a kind of continuous and smooth function between the fluid and the land or the obstacles. So with these two things solved, then what we need to do is to go from the nonlinear dynamic optimization problem to the nonlinear programming problem. So we need a kind of transcription of the control problem to an NLP problem. So what we did was we discretized the time. We have steps of equal size, and we have a Taylor expansion to solve the equations. In our first paper with the mixed integer nonlinear programming, we tested different levels of detail of these expansions, where we consider, for example, the gradient of u with the position. In this case here, the gradient of the current with respect to the space and time, it is ignored, because as I'm going to show you in some data in a case study, the current is slowly changing at the resolution that is afforded by our data. So with this, we get into an NLP problem that has this formulation, right? So we want to minimize the time. We have here the current with our function, and this function here says that this g function should be greater than 0, and this will ensure that the vehicle is in the water all the time. It is a non-convex formulation, and without the algebraic form for the current and this characteristic function to avoid the obstacles. There is still one detail in this formulation that it will disappear when we go to the stochastic programming, but it is present here. That is the final time here, it is a variable. And at the same time here, it defines the final conditions for the position. This X variable, in fact, gives us what is the position of the vehicle in 2D or 3D, right? So to solve this approach, to solve this problem, we have developed a comprehensive solution approach that is detailed in our paper in Ocean Engineering, where we have an initialization procedure because it was very difficult to find an initial solution for this problem. We have a diversification search procedure that forces the optimization to take different paths to try to get a better solution. And then we have an optimization procedure to handle this thing of the final time. So basically, to handle this final travel time, what we do is we calculate what is a lower bound of this final time. And then because we discretize the time, in parallel, we do a search over these discrete times, starting from our lower bound. So it is an algorithm that in fact solves a sequence of problems to do some initialization, and it goes also in parallel for the diversification search. Overall, in terms of the integration of data, model, and solver, what we have is our OGCM data, the matrix. We create the function with the current and the function for avoiding the obstacles. The gradients, we integrate these with our NLP model. We have the motion and planning data, and with our NLP solver, we get a solution, right? So what I'm going to show you now, it is an example of a case study, in fact, here for the Gulf of Aden. There are some details here in terms of optimization, but what I will show you is the results of two instances where one instance we navigate against the flow, and the other instance we navigate along the flow. Okay, and so what we are going to see is two AUVs that will show up here. Okay, they just, and I will stop here. We just swap what is the starting point and end point between them. And so what you can see here in these results is the adaptation of the trajectory to the current. The yellow one is kind of navigating against the current. So this yellow one is kind of hugging the seabed, right? Where the velocity of the current is smaller against. The green one, in fact, is taking advantage of the current. The vectors here give an idea of the magnitude of the current. So what happens is that the green one will go up to take advantage of the current, and the yellow one keeps down just to avoid the current, right? And that is the kind of solution that we have. We just change the starting point and the end point, right? And we see that the solution is able to adapt to the current. So after this first initial model, what we did was, let's extend this type of formulation with a multi-objective time energy objective function, right? So we added another objective function that tries to give us an idea of the energy consumption of the vehicle. And to solve this type of problem, we have a solution approach that starts by discretizing the problem, as we did before. We use the same initialization and diversification strategies that we developed for the nonlinear optimization, but now we have to handle two objective functions. And to handle these objective functions, what we did was we use a well-known method that is called the Epsilon constraint method to handle both objective functions. And what we end up is having a Pareto optimal curve, right? Where if you want a minimum time solution, you have to consume a high value of energy. And as you increase the travel time, you decrease the energy consumption. So what we did was we developed an algorithm that starts by minimizing the travel time and then systematically increments the travel time and finds what is the minimum energy consumption for that travel time. One interesting thing that we see in the literature, but we did not find in our case studies, but we see that in the literature, is that as you increase the travel time, then in fact, you can increase the energy consumption. In fact, we have these cases in some synthetic cases, but not in the Red Sea. And that is very interesting because that means that if you increase the travel time, somehow you have to spend more energy to have the vehicle on the water to get to the destination. But in our case, you are going to see that most of the curves are here, even though the algorithm that we have developed, and you are going to see a detail of that algorithm next, it accounts that the energy can go up also as you increase the travel time. So here, so what we do is we increment the travel time systematically and find the minimum energy consumption. To do that, in fact, what we have is to solve a problem for each travel time, right? And for each travel time, we change what is the upper bound on the energy consumption, right? And so we are kind of decreasing the energy consumption upper bound or the maximum energy consumption for a fixed travel time until we cannot get a solution, or we are increasing the energy. And that's why this M here, it has a plus sign, because this M here, it can be either negative or positive. And so we have an algorithm to detect if we should move up or down, if the energy consumption is increasing or decreasing. So let me show you a case study when we try to do this multi-objective optimization for the minimum time and minimum energy. So here we have a current for the Gulf of Aden. And what you see here is on the horizontal, you have the variation of the current with the time. And in fact, from time 0 until time 3 days, there is not a significant variation. So there is not a significant variation with the time, but in fact, there is a variation with depth. So because here is like -2 meters, -100, and -400, okay? So when we solve this type of problem in this environment, what we get is in 2D first is this type of solution. So we have the starting point here on the left, right? And we want to go here to the middle, to the center of this eddy. And so here we have solutions with different times, minimum time here, right? To a solution with a time like almost 3 times the time. And you can see here what are the corresponding values of the energy. You see also here that at the minimum time, you are at the maximum velocity of the vehicle. While if you try to minimize the energy, right, you are here almost at the minimum velocity, right? And you can see also that you spend much more time here than here, right? So these are 2D results. If we move to 3D, that is what we have here. And so here we start from this point here, and we want again go to the center here, right? And here we have a solution with a minimum time and a solution with a minimum energy solution that we found. And you see some difference here at the level of the eddy. So this is the minimum time, right? And you see, let me stop here. So you see, it goes up and down, and you can see that here. But now here it is very interesting because the vehicle was kind of down, but here you will go up, right, to take advantage of this current. And at this point, when the current goes up and you want to go left, in fact, the solution tells that the AUV should go down. Okay, so now let me show you the minimum energy, because this one is interesting. So here we have the same kind of solution, but in this case it's a little bit slower because it has lower velocity. But what is interesting is that if you pay attention here to the eddy, what you are going to see is that when the vehicle gets here to close to the eddy, what happens is that the vehicle will go up almost to the surface to take advantage of the current. So you are going to see that the vehicle is kind of gliding through the current when it gets here to the eddy. So you see that the current is changing. And now it's interesting to see that the result that you obtain, it is a path that is kind of aligned with the current. Okay, and so this is the kind of results, right, that we want to see. We want to check that our optimization is providing paths for minimum time and minimum energy that make sense. So in terms of Pareto curves, what the results that we have for the Gulf of Aden is like, as you increase the travel time, you decrease the energy. In 2D, we didn't have any problem with the initialization. So here we have different initialization strategies, and they are all above the same line. But in fact, here, the initialization strategies played an important role in getting this kind of better or best known Pareto optimal curve. So now let me move to our approach that involves risk awareness, but also multi-objective optimization. In the paper that we have that was recently accepted, we deal with multi-objective optimization. Here, I will only show you and try to describe the formulation for the minimum time formulation. So what was the objective and what is our approach? So what we wanted to do was to develop a stochastic optimization formulation that accounts for the uncertainty of the current. And the other thing that we wanted to do is we want to use ensemble-based forecasts. So what is an ensemble-based forecast? So an ensemble, it is a group of forecasts for the same period. So these ensembles, they are obtained by perturbing the initial conditions or some of the parameters of these models, forecasting models. And so at the end, we have an ensemble with 50 members. That means that we have 50 forecasts of our current for the future, right? So we want to leverage this information that we have on these forecasts and include this information in our model. The other thing that we wanted to do is to include a risk measure of long travel times or high energy consumptions. Usually when people talk about risk, they say, oh, we want to minimize the risk. And I always ask, minimize the risk of what? We always want to minimize the risk of something. In this case, we are minimizing the risk of long travel times, right? So what is our approach? we are going to reformulate the stochastic optimization problem into a stochastic programming problem. And I will try to explain what are the characteristics of this stochastic programming problem. So what we are going to do is to merge into one optimization formulation all the forecasts of the current that we have. Okay, so all the constraints that we have in the deterministic model now will be defined for each ensemble member, for each forecast. And because now we have these different forecasts in the model, the objective function is a measure of some property of this forecast. And what in this case, what I'm going to show you is a measure of the travel time over all the members of the ensemble. But at the same time, what is interesting in this formulation is that we have all the forecasts, the different forecasts, 50 forecasts of the current in one model, but we want to determine only one feasible solution that is feasible for all the ensemble members. Okay, we don't want to end up with 50 different solutions, one for each forecast. We want only one solution. So what is our approach for this? So we are going to use this stochastic programming framework where we have all the forecasts in the same model, but we have a decision framework that is divided in two stages, where we have first stage solutions and we have second stage solutions. So what is our first stage solution in this type of problem? It is the path. So what we want to do is to find a path that is feasible for all the ensemble members that are in the formulation. Okay, so assuming that we have the 50 forecasts, the path will be a sequence of waypoints that for any of these forecasts, the vehicle will be able to reach or to follow that path. Okay, so you will find solutions that are feasible for all. And if there is a solution that is infeasible for one of the paths, that solution is not selected, right? What are the second stage decisions? So the second stage decisions are also called in the stochastic programming framework, they are also called recourse actions. So are the recourse actions that are going to be taken for each realization of the uncertainty in our problem. So the second stage decision in this problem are the velocity, the acceleration, and the timing. What this means is that the path will be the same for all the members of the ensemble, but the velocity and acceleration and the timing variables are indexed to the forecast. In terms of objective function, what we consider is an objective function that combines two risk measures. And the risk measures are an expectation operator, a risk neutral measure, and a risk averse measure that is the conditional valued risk. And what we do is we combine these two measures into one objective function. So what is the conditional valued risk? So the conditional valued risk is a risk measure that was developed let's say, in the financial world to try to solve a problem that exists with the valued risk. So the valued risk is non-convex, and the conditional valued risk, in fact, is a convex function that let's call it with coherent properties that are very amenable for optimization. So what is this conditional valued risk? Generally speaking, this conditional valued risk is the average of the travel times above a given quantile. So let's say that is in our case, that we are minimizing the travel time, is the average of the 10%, if you set alpha or of 10%, is the average of the 10% worst travel times. So you are not only minimizing the expected travel time, but you are also kind of minimizing a combination of expectation and conditional valued risk, or only conditional valued risk. Because in the objective function, what we do is we create an objective function that is a combination of the expectation of the travel time and the conditional valued risk weighted by this beta factor. So if we set a beta value of equal to 1, then we are minimizing only the expected time. If we set a beta if equal to 0, then we are minimizing only the CVAR. And so for the minimum time problem, this is the formulation that we have. We have an objective function that minimizes the expected travel time and the CVAR of the time. We have travel time calculated for each ensemble member that depends on the forecast of the current. We have timing for each waypoint, and the kinematic constraints are defined for each ensemble member. However, note that the X variable, that is the position, it's only indexed to the grid point. So it's not indexed to the scenario of the current, because the position will be the same for every current that we consider in our formulation. So this is I think that this is a very interesting approach, because you try to find a path that is feasible for all the forecasts of the current that you have, right? But so how do we assess the solution of a problem like this? And what are the other alternatives to solve this problem? So the first alternative is what we did in part 1 and part 2, right? That is, in fact, we solve the expected value problem, where you use only the average flow field in your model. So this gives you the expected value solution. But now you have this expected solution, and you can pick this expected solution, that is, in our case, the path, and you can solve an optimization problem where you fix the path and you solve this problem for each forecast of the current that you have. So you solve 50 problems with the path fixed with different currents that are your forecast, and you can calculate what is the expected time for this problem, and that is what we have here. So meaning, use the average flow, get a path, and then fix that path and solve the problem for each current with the path fixed. An alternative that you can do is what some people call a scenario approach. You pick every forecast that you have from these 50 members of the ensemble, and you can solve one problem to minimize the time for each forecast that you have, right? At the end, you can calculate what is the expected time of all these problems. But the problem of this scenario approach is that you end up with 50 different paths. And now the question is, which path do you select? In fact, Omar has a previous paper that tries to solve this solution, right? So how do you select the proper scenario? In fact, if you look to this framework, this framework is used, and you can apply this framework to many problems, like for energy problems, right? You can solve for the expected demand, or you can, and then fix your demand and see what happens. You see a lot of scenario approach where people solve the problem for different scenarios, but then how do you pick what is the solution of your problem if you have many solutions, right? And the solution in our case is the path. Using these two definitions, in fact, you can assess the value of your stochastic solution using something that is the value of stochastic solution. That is that average of the times obtained from the expected value solution minus your stochastic programming solution. And you can calculate another thing that is the value of perfect information that will give you an idea of, let's say, how much money you should pay for perfect information, right? If you can have perfect information. So now let me show you some results in a 2D synthetic case study. So in this first case study, what we have is an ensemble with 50 members of the flow. It is a flow with a composite of vertical shear and a cosine function. You see that the function here goes from the right to the left, here from the left to the right, right? And this is only 2D. And so we have different scenarios where there is a shift on the current, on the position of the current, right? And the results that I'm going to show you, and I will put this video running so that we can better understand what is happening and better explain the results. So here is where I try to show the difference between all these problems and the value of the stochastic solution. So if you do the trajectory planning with the average current, for this case study, this is the path that you obtain here, okay? And the solution that you obtain is this red dot. If you pick this path and fix this path in optimization problems, one optimization problem for each forecast of the uncertainty, you get each of these blue spheres, okay? If you solve the stochastic programming problem with all the forecasts in one problem, and with a risk neutral solution, you get this path here. If you go to the other extreme and you minimize only the 10% worst times, you get this path, right? And the yellow spheres is the solution that we obtain from the optimization for each current. But the path in these two, note the path is the same. The dark lines, these dark continuous lines, in fact, are the paths that you obtain when you solve each scenario individually. And what we try to show here is the difference in terms of path that you obtain when you use a stochastic programming formulation. If what we are seeing here, right, is the distribution of the solutions within each problem with the time. Okay, and so each of these blue lines is for one ensemble, right? And what you are going to see, and let's see at the end, is that in fact the red line, the red dot, it will be the first to arrive. Then it will be the green. But what is interesting here is that what you are going to see is that the red line was the first. On average, the green is faster, but in fact, the yellow, these last worst times will get there before, because in fact, in this case, we were trying to minimize the worst times. Okay, and then the blue is when you are trying to optimize for each scenario with the path fixed. So another case study that we have here is a stochastic double gyre case study. Again, you see that the current for, this is a stochastic double gyre. The current for the expected solution, that is the average current, is here. And when you do stochastic paths, you obtain these paths, which are different. We obtain also the Pareto curves for energy travel time. And where here you have fixed the travel time, and you have a distribution of energy consumption that in fact depends on the forecast of the current. This using a risk neutral approach, right? And this using a risk averse, where you only minimize the travel, where you minimize only the 10% worst travel times. In this kind of result, the other thing that we get is the value of the stochastic solution, and where we see that we always have a positive value of our stochastic solution. And you can also study what is the value of the expected travel time and C-var of the travel time as a function of the beta parameter that weights both functions in the objective function. And so what you can see here is that if you pick up a beta of 0.2, you don't pay much in terms of expected time, and you reduce the C-var of the time. If you go to really risk-averse solutions, what happens here is that you increase your expected travel time at the cost of minimizing the travel time of the worst cases. We have another example for the Gulf of Aden, where we do also a stochastic approach, right? So we start here and we end here on the left column, and on the right column, we start on the left and end here. So what we can see is that depending on where we start and end, we obtain different paths. This shows that optimization is able to adapt to the current, but also depending on using a more risk neutral or risk averse approach, we obtain different paths as solution. So as a review, what we did was what we are doing, we are developing trajectory planning models, nonlinear optimization models, and integrating the OGCM data that we get that we get. We extended these for time energy multi-objective framework. We have detailed algorithms available in our papers to account for non-monotonic relations between energy and time. And we were able to extend this nonlinear formulation to an ensemble-based stochastic programming formulation that I think that it gives very interesting results comparing this expected value path with the path from the stochastic solution. In terms of final remarks, the results, what they show, in fact, is that the models and the solvers, they lead to solutions where the paths and the trajectories are adapted, and trajectory in terms of x, y, depth, and velocity, they can adapt to currents to minimize the time or minimize the energy consumption. We see also from the results that stochastic models give paths that are different from the average solution, and that risk neutral and risk averse solutions lead to different paths. And this ends my talk.
So thank you so much, Dr. Ricardo. That was extremely interesting. So thank you so much for your talk.